Uh, Hello and welcome everyone to the Earthquake Engineering Research Institute's Friedman Family Visiting Professionals Program 2021. This event was supposed to happen last fall. Jim we were allowed to have Jim last fall, but due to the COVID thing, it had to be a virtual event. And we're lucky enough to have him even through this medium now. Uh, I'm pleased to announce that we finally have Jim with us. He is the senior principal with Degan Kolb Engineers of San Francisco, California. He received both his bachelor's and master's degree from UC Berkeley as a registered structural engineer in California. Mr. Malley has over 30 years of experience in the seismic design, evaluation, and rehabilitation of building structures. Uh, Another outstanding achievement I'd like to note, first of all, is that the election to the National Academy of Engineering is among the highest professional distinctions accorded to an engineer, and Jim was recently awarded this prestigious honor. So we all would like to congratulate him for this prestigious honor he got. Uh, the presentation today will be about performance-based earthquake engineering of tall building projects. Jim will be shedding light on some of his selective peer-reviewed projects to discuss on some of the unique features and interesting findings related to those projects. So this presentation comes at a time when performance-based non-linear uh, seismic analysis has already been established as the most reliable method for both design and retrofitting of old and new structures. So let's get the insights from someone who has been there and done it since the past three decades. And let's welcome Mr. James Maddy.
Thanks, Alok. Appreciate it. And sorry we can't be together, but it's been my second trip to KU to give a presentation. I was there a number of years ago to speak at your big spring seminar. So sorry I can't be there today, but hopefully this will still work out. As Alok said, I'll be talking about tall buildings and design, seismic design, performance-based design topics. I've actually split the presentation into two parts. The first part is going to be on what is being done on the West Coast for these new designs of tall buildings related to performance-based earthquake engineering. And the second half, I'll be focusing on existing buildings, existing tall buildings, and a lot of studies that our company has been doing on older tall moment frame structures that were very prevalent in the 50s, 60s, 70s, 80s, and into the early 90s as office buildings in San Francisco, Los Angeles, et cetera. So we've had some interesting findings about those, and I thought that those would be interesting as well. So that'll be the two topics, but what I need to start with is to talk about EERI and why I'm here in the whole program. So there'll be two different presentations. I'll start with a quick one first on EERI, and then I'll give the main presentation. And so let's see, I'm going to share my screen here, so hopefully that will work. And I'm going to share screen 2. Okay, so hopefully you can see that screen now. And let me go to the presentation mode. That'll work. Okay. So
it's not being shared right now.
Not being shared? Oh, you know what? I think I have to hit it. On Zoom, you have to hit it twice, right? Some of the other, okay. How about now?
Yeah, now it's open.
Okay, great. All right, so now I got to go to presentation mode. So I don't see everything else. Okay, so we still good? All right, cool. All right, let's jump into it then. The Friedman Family Visiting Professionals Program is a great program that EERI has had for a number of years. David Friedman is one of EERI's past presidents and generously donated some money to EERI to promote this program. And so visiting professionals are invited to visit campuses all over the country to talk about EERI and its activities, as well as kind of earthquake engineering in general. So part of this is to give a short presentation about EERI. You can see established in 1948. The interesting thing about EERI is that it's very cross-disciplinary. That most of the people that are members are structural engineers, but there are geoscience people, there are social science people, architects, planners, emergency managers, etc. So it's a great place for people that are interested in earthquakes to interact, because it is a topic that cuts across sort of many different professional disciplines. So this is really the place where you can get involved on that scale. Okay, so mission statement, you can see here: to advance the science and practice of earthquake engineering, improve the understanding of the impact of earthquakes on social, economic, political, cultural environment, advocating for comprehensive and realistic measures for reducing the harm of earthquakes. So it does move away from the very technical parts into the political realm and the public policy areas. Really, EERI makes a great contribution in that area. So it's a great place for technical people like engineers like me to be involved with folks and help to move processes forward that can make real change for the communities we serve. So why is it important to join EERI? Again, to connect with all those people in different disciplines and stay up to date with the things that are going on in the earthquake engineering world. There's lots of different ways to get information, whether there's through the peer-reviewed journal. Spectra is a wonderful journal, one of the best probably in our profession for getting information about earthquake engineering. Very high quality papers in that journal. Webinars, post-earthquake investigation, presentations, seminars, as well as every 4 years there's a major national conference that's held to bring the whole community together. You can see this is a great place for young people to get involved and then have opportunities to potentially to become into leadership positions within EERI. So my story with EERI. So when I first started working at Degenkolb out of grad school, there weren't any student chapters, but Henry Degenkolb was actually one of the people that helped found EERI. And so it was very much ingrained into the culture of the company that you would join EERI when you started to work with the company. So I did. And then about 9 or 10 years after I started working, there was an earthquake in Erzincan, Turkey, which is in central Turkey, probably just about right on top of the North Anatolian Fault, which is very similar to the San Andreas Fault that we have in California. There was this Erzincan was right on top of the fault, and the epicenter was within a mile or two of the town center. So it was hit very hard by the earthquake, and EERI dispatched a team, and I was asked to participate on that team. And so I spent about 10 days there. And it was an amazing experience to see how the city had been affected and how it was trying to react or respond and recover in those early days afterward. And then we ended up writing a report. The team wrote a report about what we learned that was then shared with seminars by EERI around the country. And I've been involved in the national conferences. I mentioned that since 1984 in annual meetings. I actually co-chaired the most recent national conference that we held down in Los Angeles in 2018. About 1,500 people were there, met for over 4.5 days of lots of great presentations and learning that went on. I think Elena was one of the presenters there at the conference. So it was also involved with technical seminars committee for a number of years, was on the board and was vice president, came off the board about 3 years ago. So again, who are the members? Very cross-disciplinary. You can see, can connect into earthquake engineering from a lot of different areas or areas of practice or expertise. So it's a very, like I said, one place that's really is multidisciplinary of all the technical organizations that we might join. A few things that the organization does that are proud programs include the SESI, the Schools Initiative, Safety Initiative. So it does outreach and screening, education and policy, working with teachers and parent organizations, et cetera, to inform them about how to make schools more safe in earthquakes in various regions around the country. The Learning from Earthquakes program has really been sort of one of the sentinel programs of EERI. For many years, it was funded by NSF. It's now more self-funded. And so in a lot of ways, it gives people an opportunity to participate in earthquake reconnaissance. It's an amazing learning opportunity to be involved with these earthquake reconnaissance programs. Seeing things firsthand is, there's nothing like it really, as far as your education and then learning from, seasoned professionals that can point out things that you might not see if you just looked at something by yourself or looked at a picture. So it really is an amazing program. And if you're interested, this is a great way to join into EERI. Then there's an LFE travel study program that for students where you can go on field study trips to earthquake regions. This would not be right in the aftermath of the earthquake, but some months later potentially, where the team puts together a topic that they want to address or look into more deeply and spend some time on site and make connections ahead of time and learn more about some detailed issues that they would like to learn more about. So student member benefits, this program is one. The seismic design competition, I'm pretty sure KU participates in that. It's a great program, a lot of fun. People really enjoy that. It's some of the annual meetings, there are as many students there for the seismic design competition as the professionals, which is really great, brings a lot of life and energy to the annual meetings. There are student papers and fellowships, graduate fellowships, also that can be recognized for students. And you can see travel grants are available to attend the meetings, as well as access to the online Spectra, which is the technical journal. And then after graduation, you can, if you go on to graduate school, join the Student Leadership Council. There are many young members committees, and we'll talk about regional chapters in a second. There's a young members committee that covers all of EERI, but then there are also regional chapters, and some of those have young members committees as well. There's regional chapters. You can see the seismic design competition. You can become a mentor to the team, potentially your school or another school if it's local to where you end up working. Postgraduate internships are also available through EERI in the office in Oakland, California. And then we mentioned the LFE study trip. So lots of places where you can connect into EERI after graduation. So here's a list of the regional chapters. Many of these are quite active locally and participate in policy issues on the local levels with different cities in their region. And they have regular meetings to talk about issues that are going on locally, as well as in the larger scale of the EERI. So one nice program about continuing membership is first year after graduation is free to student members, and then at highly reduced rates for the next 4 years afterwards. So hopefully companies will support membership as well, but EERI does want to continue to draw forward the students as they become young professionals. So the website eeri.org, you can find out a lot more. But again, I want to thank EERI and the Friedman Family Visiting Professionals Program for allowing me to make the presentation today. So with that, I will get out of this one. Oops. And see if I can. Okay, and hopefully I'm still sharing. Still sharing? That look okay? Okay, cool. Great. All right, so let's get into the meat of the presentation then. Seismic evaluation of existing tall building projects using performance-based earthquake engineering. Actually, it's not just existing. I should have got rid of the word existing, just tall building projects using performance-based earthquake engineering. So as I mentioned, 2 parts. First part is on performance of new tall buildings. And I'm going to go through sort of how the process works, and then talk about some specific examples of projects that I've been involved with as a peer reviewer, which is a big part of this whole program. So just want to start by we use guideline documents, and I'll go into those in a couple of minutes as far as, but kind of in a lot of the projects we've been looking at are what we call core wall systems. So many of the large condominium towers, apartment towers that are going up in major cities on the West Coast have a primary lateral system that is reinforced concrete shear walls around the elevator, stairs, mechanical shaft core of the building. And this system is really not allowed by our building codes right now in high seismic zones over 240 feet, unless you have a moment frame system, a sort of a dual system, is what's allowed for taller buildings when you want to use a shear wall building. So architecturally, that presented challenges with the idea of getting full sight lines from condominiums, et cetera. So they didn't really want to have a deep kind of reinforced concrete moment frame around the perimeter of the building. So the engineers started to wonder if they could go outside the bounds of the prescriptive building codes and try and do just the core of a reinforced concrete lateral system and be able to demonstrate that it would perform properly. So traditional code design is built on prescriptive rules and linear analysis. It's sort of been built up over the last, almost 70 years now, 75 years. And it really has grown over time, become more and more complicated, but still is based on some pretty simple concepts for earthquake design. So we're really trying for life safety for most all the buildings. We really think that many of the buildings have more capacity than what we give them credit for in the building code. Again, because it's a fairly simple procedure, you're going to be a little more conservative on things. So we asked questions like, how much capacity do we really have? And we really don't have a great idea how big an earthquake it takes to really, and bring them down is obviously a pretty, we really don't want to think about collapse, but we want to know at what point our structures are really going to be vulnerable to severe damage in an earthquake. And the code really can't get us there. So we needed to think about this a special class of buildings because the building code doesn't really address very well long period structures, which have modes of response that are different from what's the simple approach that's covered in the building code. P delta effects, when you get into large displacements, become more, when you have longer periods, you can have larger displacements. So P delta effects become more important. And that is an important consideration for the collapse potential of tall buildings. Obviously, can potentially have large occupancies, especially if these are used for office buildings. And that could impact not just the building if there's a collapse, but all the surrounding buildings around it. You can imagine having to cordon off after an earthquake. If there was major damage to one of these buildings, you might have to evacuate blocks in all directions around the building. So we've also come a long way in our ability to do analysis. We go from a linear static to linear dynamic to nonlinear static and dynamic, and from deterministic kind of one level of demand to probabilistic, where you use multiple levels of demand in order to understand the performance of our buildings. And the ability of computers to do all of the calculations that we never could do before, and manage the data in ways that we never could imagine before, really allows us to move forward with this type of more detailed approach and analysis than ever was possible. So some more on why performance-based for tall buildings. Code, we kind of talked about it before, the codes really weren't thought about with specifically with tall buildings in mind. You can see here sort of a graphic of really like 1% of the buildings built in the United States are taller than 14 stories. So when you get up to 30, 40, 50 stories, you're talking about a very small fraction of the number of buildings. So the fact that the building codes do not really kind of target this small sliver of the pie, if you will, makes sense, right? So and engineers recognize that now, and now we're trying to search out better ways to design these buildings. The building code also thinks about specific building types that have been used over the years, and there's a list in the building code. In ASCE 7, I think there's 82 different building types, but engineers can come up with all kinds of different ideas for how to put together structural elements to resist earthquakes. A couple pictures here. I'll talk about both of these as we go forward. So there's how you understand system performance outside of building code definitions becomes very challenging. And there's some ways to do it. There's a FEMA P695 approach, which requires hundreds and hundreds of nonlinear analyses or maybe thousands and thousands to sort of pre-qualify another building system. For an individual building, that just doesn't make sense. So we wanted to get a more reasonable approach using some what we call capacity-based approaches to design, which are incorporated into the building code in many ways, and continue that in looking at some of these more unique structures. And really, one of the things that's important is to really think about is for earthquakes, it's really much more important to think about deformations than it is about forces. Most of the building code requirements are force-based because, again, they go back far into the distant past. But really, when we think about earthquakes, we really want to be controlling deformations, because deformations, that P delta movement, is what really brings buildings down. And so that's what we have to be focused on. So luckily, the building code has a way for us to work outside of the prescriptive requirements of the various standards. And you can see in red here that alternative materials, methods of design, etc., can be approved by the building official if they find the proposed design is satisfactory, complies with the intent. So at least equivalent. And that allows engineers who are brave to step outside the building code and come forward with a different design approach and then try to get it approved by a building official. So ASCE 7 has a similar clause that allows the engineer to bring forward new ideas and to bring forward an approach or a system that's not specifically permitted by Table 12.2.1, which lists all the permitted systems, if you can show that you have similar performance that you would have from one of the defined systems. But there's a somewhat of a problem with this. So how do you establish equivalency, or how do you establish if it's even better than what code performance is? So you need some kind of a methodology, and how do you establish what's the acceptable seismic hazard with the methods to do that? What's the acceptable modeling and analysis techniques, because we are going to be going beyond linear analysis now, and what's a rational acceptance criteria. So guidelines have been established over the last 10 or so years. And the two primary ones are the two on the right here, the PEER, which is the Pacific Earthquake Engineering Research Center Tall Buildings Institute guidelines, as well as the Los Angeles Tall Building Structural Design Council guideline document, which is the one on the right there. Some of the cities, like San Francisco has put together some administrative guidance on how to do this, but not the technical work. And then the fourth document here is in the second one from the left is from the Council on Tall Buildings and Urban Habitat on tall building design. Very general, it's good information, but really isn't directly helpful to engineers trying to accomplish one of these designs. So as I mentioned, the PEER Tall Buildings Institute guideline and the LATB SDC guideline are the two most widely used. They work with ASCE 7 as well as ASCE 41, which is a document on the seismic evaluation and retrofit of existing buildings, which has a lot of performance-based concepts in it, and some also ETC documents that were sponsored by NIST on nonlinear modeling approaches. And the latest one is ATC 114. And it's now a NIST report, but I can't remember I should have written that down, but I can't remember how that goes forward. But if you type ATC 14 into Google, you should be able to find those modeling approaches if you're interested. Each of the jurisdictions that I've worked with kind of deal with this a little bit differently. One thing that's very common to all the programs or all the cities is that they get a peer review panel. Generally one or two engineers, a structural engineer, practicing structural engineer, oftentimes an academic practicing or an academic that has expertise in the type of structural system that's being proposed for the building, as well as someone that's an expert in ground motion development, because we have to develop ground motions to simulate the kinds of earthquakes that the building will be subjected to. So each of them do that a little bit differently, but that program is always in place. So performance objectives is a little bit different for the guidelines than code-based approaches, where we generally have one level where we look at a 10 and 50 or a 475-year return period event. For the two guideline documents that we work with, mostly the PEER and the LA Tall Buildings, we have two levels. We have a serviceability earthquake, which is a pretty small earthquake, frankly, 50% in 30-year chance of exceedance. And for that earthquake, we basically say that the building needs to remain elastic. So we check it for using elastic procedures to make sure essentially that the building is performing, or the models are performing the way we would think they should be. since we have a lot of background in elastic analysis. And then going forward to the very rare event, which is what we call the maximum considered earthquake. And that is a 2% in 50 response period generally. And a very large earthquake, the largest that you would consider being possible in the region that you're in. The ASCE 7 Chapter 16 now has guidance on how to develop that. It didn't in the past, and that was partly developed by the guidelines, and then ASCE 7 picked that up from the Pure TBI and the LA Tall Buildings guidelines. So that's now in the code, which is nice. It also includes criteria for higher risk category buildings. So risk category, if you're not real familiar with the building code, so risk category 4 buildings are like police stations, fire stations, hospitals. Risk category 3 are generally very large buildings that have large occupancies, either for assembly or for the number of people within the building at any one time. And so because they have more people, or we want them to be functional after an earthquake, there are larger, higher performance requirements for those higher risk categories. You can see the targeted risk of collapse for the different categories down on the bottom there. And you can see as we get out to risk category 4, we're talking about a 2.5% chance of exceedance or risk of collapse given this very, very large earthquake. So still a very large or very small chance of collapse, even given the largest earthquake that it could occur in the region. Talked about capacity design. I mentioned that a little bit ago. Very important conceptually as we're putting together seismic design systems and configurations for buildings. And we'll talk a little bit about that in the next couple of slides. The idea is that we want to control where the nonlinear response in the building is going to occur during the earthquake. We can't design for this biggest earthquake that can be considered for the building to remain completely elastic. And because we wouldn't be able to design real buildings in effect, because there'd be so much structure that there wouldn't be any windows and things like that. Nuclear power plants are about the only thing that gets designed to be elastic for this very, very large earthquake. So we know we're going to have some inelastic behavior. We want to control where that's going to be, and to make sure that everything else around that, those inelastic elements, are going to remain elastic, and make sure that then they hold up the rest of the building. So some of the things we got that covered. All right, so what we do then is we classify the structural actions as either force controlled or deformation controlled. So the deformation controlled are the elements that we are expecting to yield and deform nonlinearly in an earthquake. And the force controlled are the ones that stay elastic and sort of make sure that they're stronger than the deformation controlled elements that they're connected to. So we sort of limited the demand on those elements, because, and you'll see in the second here, there's 3 categories for the force control. And then we can look at a few images here of some systems, a moment frame on the left, a concentric brace frame in the center, and an eccentric brace frame on the right, where the red elements are the deformation controlled elements. And so those are the ones that are going to yield and inelastically deform during the earthquake, dissipate the energy. And the other elements, the braces on the right and columns in all the systems, remain essentially elastic so that they keep the building from going too far and really focus all the energy dissipation where we can guarantee ductility and good inelastic and earthquake response performance. So when we think about the deformation controlled elements in our nonlinear models, we let those go nonlinear. We watch their deformations. We make sure that they are within the bounds of what these elements have been demonstrated to deliver in tests that are done in universities around the country, whether it's a moment frame connection or a link beam in an eccentric brace frame, or buckling, the deformations in a buckling restrained brace in a brace frame system. So let's see, yeah, I think we can just go past that. So on the force controlled side, the way we talk about critical, ordinary, and non-critical, and you can see here, if it's a critical element, if it fails, it could, result in a major collapse of the building. So imagine a very important column in a building would be a critical element or a part of the structure. Some of the other ones are checked for less demanding criteria. If we lose them, we don't really feel like there's a significant life safety hazard. So when we look at the ground motions, we have different criteria depending on what risk category you're in. Many times now we are doing, on these tall buildings, we generally do 2 suites of 11 ground motions. We can't get into why 11, it's sort of a strange number, but there's some statistics behind it. Generally 2 suites because they do have significant second mode of response that can control the design, that if you only do 1 suite of ground motions, the ground motions really won't be targeted or characteristic to the 2 primary modes of response. So we've kind of gone to this, what we call a conditional mean spectrum approach or multi-suite approach. So when we do these nonlinear analyses, if you do run into one ground motion that seems to go beyond what we consider acceptable deformations in the structure, we've determined that you still can be demonstrated to have that acceptable level of chance of collapse given the MCE earthquake. For the higher risk category, we don't allow any of those sort of ground motions to exceed the criteria, unless on risk category 3, you can see 20 ground motions instead of 11 have to be used, which doesn't really seem to happen in practice. Okay, analysis. So there are a number of checks that we have to make on each individual analysis, and I won't read through all those for whether or not the model has, kind of given us acceptable performance. And a couple of the key ones are the maximum drift that the building goes through, the interstory drift, which is the deformation between 2 stories, or the residual story drift. So that's when the earthquake is over, and if there is some out of plumbness of the building due to residual drift. And this is the first time in seismic engineering in the United States that we've ever been able to check or been asked to check on residual drift. And it's a very hard thing actually for us to estimate accurately. And I'm still not convinced that we do it that accurately. Generally, most of the buildings we look at, the residual drift doesn't seem to control, which is good because, like I said, I'm pretty skeptical about our ability to predict this. But it's the first, and I think it's a really important thing because, again, after the earthquake, if you're standing across the street from a tall building and you can see it leaning over, if you're the building official, what are you going to do, right? And are they going to evacuate, 8 square blocks or whatever because that building, if there's an aftershock, that might mean that it doesn't have the kind of capacity left to resist a major aftershock. So luckily we haven't had to deal with anything like that in past earthquakes, but in the next earthquake, we may not be so lucky. Okay, let's go here. So on evaluation procedures, we need to develop 3-dimensional models. We need to put together realistic estimates of stiffness, strength, damping, etc. And then damping is pretty tricky for these nonlinear analyses, because a lot of what we consider damping in our elastic models, where we use a very kind of a simple rule like 5% viscous damping, that includes the consideration of the inelastic or hysteretic response of the structure, where it's dissipating energy by that yielding in those various deformation controlled elements. So we have to use a smaller, when we do a nonlinear analysis, we have to pull that out and then try and get the other type of viscous damping that could be in the building from other elements that are not part of the lateral system or the structural system that we consider. Cladding, there can be some damping that comes from cladding and other parts of the structure. And generally we're down in the 2% range especially for the tall buildings that we're working with as the damping. So that's always a point of discussion when we get into the review of these buildings. So then we have these nonlinear models, and they're generally, we use what we call concentrated plasticity models. So like a plastic hinge, if you will, for beams and columns to estimate the response of that nonlinear response of that element. For walls, we use what are called fiber models, where you can imagine if you've got a wall, you would have a series of fibers that would estimate the strain and force demands that that fiber goes through when the wall goes through lateral response. And it has, some yielding elements so that you can watch the yielding go through the different parts of the wall. So get into a lot more complicated modeling than we typically do with our elastic models. Let's see, so axial deformation of gravity columns can be important in these taller buildings and often needs to be considered in the model. And I'll talk a little bit about that on some case studies here in a second. One thing that's very important for tall buildings is that generally when they hit the sort of ground level, they oftentimes increase in size, and we call them podiums. They could be like a retail space for a couple of floors, or offices, etc. Parking garages also sometimes are above grade, or they could be below grade. So the structural system has this change in its characteristics in many of these taller buildings. And a lot of times there's what we call a transfer diaphragm that, or this way in this graphic, hopefully you can read, it says main backstay diaphragm, where that sort of becomes the base of the structure, right? And so then there's a large shear transfer out of the core wall into that diaphragm to deliver force to the rest of the new part of the lateral system that goes below the transfer diaphragm. It could be basement wall, perimeter basement walls in many cases in the parking levels. And that transfer diaphragm is probably the most important element in the entire building to understand its performance, because it can potentially have huge forces in it. And if we don't design it properly, the whole system could kind of disintegrate and have response that we weren't planning on. So we do a lot of extra study on these transfer diaphragms, different considerations of the stiffness and strength, and some very detailed strut and tie type analyses a lot of times on these, and they're often very thick, sometimes up to 18 inches thick. I've seen even 24 inches thick in some cases. So some issues with these core wall buildings, sometimes there are cases where the columns are quite close to the core. You can see in the upper right, and I think you can see my arrow there. This column here, especially, if you imagine forces going in the direction, the short direction of the core, so it would potentially put tension in the core wall corner just adjacent to that column. That column is also going to try and act as a as a tension element. So there could be some forces generated in that column that wouldn't be typically seen without modeling that element into the lateral system, if you were thought of it as just a gravity column. So there are some rules of thumb where engineers try not to get their gravity columns too close to the core, so they don't have this coupling effect where you really need to consider the extra demands on those columns. Irregular wall openings sometimes happen. You can see in the lower left here was a case where there were stacked openings and coupling in a coupled wall above, and then they sort of disappeared, and then there was this fairly large opening for some architectural reason. And you can imagine trying to transfer the forces around this region here and become quite complicated. So this is a classic case for a sort of strut and tie model that you can learn from ACI 318. There's also some other ways to model a system like that, which was used by the engineer. They did it two different ways to make sure that they kind of covered the approach. And then I'll talk a little bit about outriggers in a minute, because that becomes fairly common in some of the larger, taller buildings as well. Okay, one thing about modeling and analysis is we really want to push as far as we can on the actual strength of the elements and the structures in the structure. And this is an interesting graph that was developed by Professor John Wallace at UCLA on slender shear walls. And you can see that when we get down to potentially what he's seen in his tests is that if you keep the strains low enough, the steel strains in the boundary elements or extreme fibers of the wall, that the actual shear capacity can be increased by almost a factor of 1.5 over kind of the standard 2 square root of F prime C kind of number for the shear wall. So we can take advantage of that because many of these shear walls are fairly slender. And so we really are reaching out for as much strength as we can when we're doing these performance-based type designs. Okay, well, let's get into some of the peer reviews that I've done over the past 15 or 20 years on various types of projects, not all tall, but they all had some very interesting things to deal with. So the first one was called Pac Bell Park when it was developed. It's in San Francisco. I grew up as a San Francisco Giants fan. So this was very fun for me to work on. The building is right on the waterfront. You can see in the center piece there. It's on probably the worst soil almost in all of San Francisco. I think about maybe 30 or 40%, I think, of the cost of the structure was the foundation because it was on such horrible soil. It was so bad that they had to put in a special foundations under, even the field would have sunk. So they had to put under not under just the structure, but the field itself had to have a foundation under it because the ground was so bad. It's an interesting structure in that it is a combination of concrete and steel. The architect wanted to have all of the exposed structure while you're sitting in your seat or as you're in the concourses you'd be seeing steel because he was trying to evoke older stadium designs from the like Wrigley Field or Fenway Park days. But they wanted the engineer thought it was going to be more economical to use a concrete type frame structure. So there was some interesting challenges with the interaction between the steel and the concrete. The other thing is when we have stadiums generally are designed as individual structures with seismic joints around them because otherwise it'd be very hard for the engineer to control the design and not have damage at sort of corners and things like that. So you have multiple joints. So it's not one structure that you're evaluating, it's 7 or 8 structures because of all the seismic joints around the perimeter. Another one that was very interesting in San Francisco is the De Young Museum, which is out, if you know San Francisco, is in Golden Gate Park, out not too far from the ocean. Very interesting project architecturally. And one of the things about that's interesting about museums is if you've ever heard of the technology called base isolation. Base isolation is used to really separate the movement of the ground from the structure above the isolation plane. And museums are a great candidate for isolation because the contents are invaluable in many cases, right? It's not only does it protect the structure, but it also reduces the demand or the shaking intensity above the isolation plane to the point where you can protect, say, porcelain, glassware, that kind of stuff that is very fragile, could be protected from being damaged in an earthquake. So in this case, they isolated the main museum. They also had a very complex observatory tower that you can see on the far right that sort of twisted and leaned as it went up. So it had a tendency to potentially ratchet because the center of mass and the center of stiffness, actually the core was vertical, but the center of mass changed along the height of the building and twisted. So potentially if the earthquake started, it could have some torsional modes that might have twisted it into very damaging processes. So what the engineer did was I thought was a great idea. They actually put vertical post tensioning into the concrete core in order to keep away from sort of a ratcheting type of approach because the mass was kind of changing over the height of the building. So really an interesting project to look at. So LA Live is down in downtown Los Angeles. It's at 54 stories. It is the tallest steel plate shear wall in the world. So steel plate shear walls, the idea there was replacing the concrete core walls. Architecturally, they were looking at an all steel building, but then originally the engineer thought, well, I'll just do concrete cores, steel frames. The steel fabricator said, and the general contractor, that creates a real problem for construction when you are sharing the trades like that. And the integration between the concrete and the steel can present challenges because of issues with tolerances are tighter on steel than they are on concrete, and then the steel has to connect to the concrete. There can be all kinds of problems during construction. So they went with the steel plate shear wall in this case. Very interesting. It's an L-shaped building for 27 stories, and then just a tower for the condominiums above level 27. You can kind of see that in the picture on the lower right. There's a hotel that does the 27-story part of the L. So some interesting diaphragm challenges. Again, there's a transfer diaphragm at the roof of the low rise that creates some interesting force challenges, as well as down at the ground floor. And we can talk through that as we go forward here too. So one of the things that was interesting about the analysis here was that generally to ease the design process, design engineers typically assume rigid diaphragms. It helps to cut down the size of the analysis and the speed that you can do it. Unfortunately, in this case, when they had that L connecting in at those upper floors, there was going to be some major force transfers at that low roof. So the engineer had to modify their diaphragm design to use what we call flexible or semi-rigid, or they had to model the stiffness of the diaphragms in that region above and below that transfer at the roof in order to make sure that they properly captured how those forces were going to transfer between the core walls that are in the main tower, and then there's a lateral element out here in the far end of there's a small core out here for the hotel part of the tower. So again, a little bit of a challenge for that building. Wilshire Grand is the tallest building west of Chicago at about 72 stories, downtown Los Angeles also. This is one of the buildings where they went with a combination of steel and with a concrete core. It's a very narrow building in the short direction. So we had to do what we call outriggers, and I'll go into that a little bit more in the next slide. But they also use what we call belt trusses around the perimeter at the outrigger level to help to equal out the forces in the columns sort of all the way around the perimeter to get better performance overall in the building. It used what we call submerged arc welding in the field for some of these. There was some massive, like 2-story tall gusset plates to connect, and I'll show those on the next slide, but to connect one of the outrigger braces into the core. And this was a technique that they could do that welding much more quickly. Also had the largest concrete pour in the history of the world. I think it still is. It was a 21-foot thick mat over the entire size of the building, or the entire footprint of the building, and it was 22,000 yards of concrete that was poured in one continuous pour that took place over about 12 hours. One truck of concrete is about 10 yards. So 2,200 trucks of concrete came into that site over between midnight and 10 o'clock in the morning on a Saturday. So this outrigger concept is important for very tall buildings that are narrow. And you can see here on the Wilshire Grand project, a graphic here on the left. It is so narrow that they had to have 3 different outriggers. What it does is it basically makes the whole structure resist the sort of overturning forces that are on the structure from either wind or seismic. In this case, the wind was very important in that broad direction, the broad sort of up and down on this bottom sketch of pushing wind in this direction, very narrow in the short direction. So that basically increases the depth of the structural system out to the full depth of the building, reduce the building period from 11 seconds, which is really not good for all building design. It's really too far. We don't really feel comfortable for that long a period, down to 7 seconds. So we're increasing the overall stiffness of the building by almost a factor of 2 in order to get that reduction. So the concept on the outriggers is that you carry the loads out from the core wall through diagonal braces out to these exterior columns, and then you get sort of a wider stance for the resistance. I talked about that submerged arc welding. It was over this sort of story deep plus gusset plate between these buckling restrained braces were used here and are often used for outriggers because they have a buckling restrained braces. We can control the compression capacity and the tension capacity. And then that limits the demand on the outrigger columns. So you get a more efficient design. So that's a pretty common way to use outriggers. Okay, 181 Fremont is in San Francisco. Very interesting architectural design. It's about 54 stories. Basically the prime, and it's such a narrow footprint that the lateral system is a perimeter system. There's no core wall in this building. It would basically take almost the whole footprint in order to have that type of core wall. So what they did was they had a series of what they call mega braces. So 4 braces over 54. And actually, I think the architecture changed to only 3 braces over 54 stories. These braces were, there was a moment frame as well as this exterior brace frame around the perimeter. What they call the mega braces included as a part of it was, and say this is an 18-story long brace. the first two or three stories was a buckling restraint brace. Then there was an elastic element, and then there was a damper placed up at the other end of the brace. And the damper was important, not for the major earthquake, but for wind and for wind, so people wouldn't get seasick in the upper stories of the building when a good windstorm came through. The damping would reduce that motion. In the big earthquake, it has a locking system so that the damper locks up and the BRB works and yields and helps to take the deformations in the building. We had some transfer trusses. And the building sort of twists and leans a little bit, so it also creates some interesting issues. The engineers also designed the columns at the four corners to allow some uplift in the very largest earthquakes in order to reduce some of the demands on the foundation. So quite an interesting, challenging project. Oceanwide Plaza is in downtown Los Angeles. It has three different towers on a single podium. And so that again creates a lot of challenge for the transfer diaphragms between the three buildings and how those are going to be shaking independently and loading up the transfer diaphragms. The two shorter towers are connected for about 8 stories above the podium. And foundation mat, basement, all those sorts of elements were quite challenging on this, and it's a full city block, so it's quite a large project. That transfer issue is highlighted down here on the bottom, where we've got the main 2 cores in the main tower, and then a core around each of the smaller towers, loading this large podium that also has perimeter shear walls. And how you do the interaction of those and design those can become quite challenging. Some other interesting podium transfer challenges on the LA Live project here on the upper right. This is actually in Professor Jack Malley's book. He was one of the peer reviewers with me on that project. The architecture said that at the cores were here where the main lateral shear walls were for the tower. And then when they hit the podium level, the architects for some reason needed the escalator to get from the basement stories to the main kind of plaza level, right adjacent to where the main force transfer needed to be to get the loads out of the core, the tower cores, and deliver them into the large podium. So instead of delivering it back through where it wanted to go through into the main part of the podium diaphragm, they had to take the loads out into this shorter region, use a strut and tie model to push the forces to either side of the openings, and then drag it back into the main body of the transfer diaphragm. Tremendous. I've never seen so much rebar in any piece of concrete in my life as in this transfer diaphragm. So architecturally, if they could have moved that over, 3 or 4 feet, they could have avoided all that challenge to the engineer, but apparently not. Anyway, those kinds of things happen in these podiums. Some risk category issues. This is on that Oceanwide project. The towers themselves could be categorized as risk category 2 because they're condominium towers, not that many people involved. But then once the building hit the podium level, all 3 of the towers count as being part of the occupancy for that. So what the city ended up saying was, okay, you can design the towers above the podium as risk category 2, but then everything from the podium down has to be risk category 3. So that the engineer had to go through lots of different analyses to check the towers, and then differently than they check the podium and the foundation. So kind of a strange approach, doesn't really make any rational sense from an engineering perspective. but from a code perspective, the jurisdiction felt like that was the best way to deal with one of these multi-tower systems. So Rainier Square is in Seattle. It's an 850-foot tower. It's now the second tallest building in Seattle. Very unique architecture here. You can kind of see the swooping architecture here. And then the other thing that's probably the most important about it is it's the first application of a new system that's called, the AISC is now calling it Speed Core for marketing purposes. What it is it's a sandwich plate system where you have a steel plate on two sides separated by tie rods in between at close spacing. And then you fill the center part with concrete. So you can kind of see that graphically here from some tests at the University of Buffalo. And the nice thing about this is you don't have to have rebar. It's just poured concrete down and the steel acts as the reinforcing. And so it can be quite an economical system. I mentioned the challenge between steel framing systems with concrete cores. This allows the steel fabricator erector to have control over the entire building height and not have to work directly with a concrete sub, because all the concrete sub has to do is pour concrete down the inside of the voids between the steel plates. So it worked out. It saved I think 11 months in construction of this building because of that change in philosophy. Very interesting design. A lot of fun to work on that one. Oceanwide Center is in San Francisco. This building is under construction right now. Some more of this exterior mega brace type of approach. Some faceted architecture on the front of the building. There's two towers. There's also a condominium tower in concrete, as well as the 50-story steel building. Probably the most interesting part about this design is the first six stories, I believe, are open. There's no, it's like an open plaza underneath 50 stories of office tower on top of it. So it's intended to be a gathering area for people to have lunch or do whatever, and then enter the building. The first occupied floor of the building is the 7th floor. So kind of an interesting system to try and make sure that the whole entire building works together. And then last but not least, the Wrapper Tower. This is being erected right now down in Los Angeles near the LA airport. Supposed to evoke the bird's nest down in Beijing, if you remember the Olympic Stadium. It's a series of built-up boxes of steel that are 2 feet wide by 1 foot deep that wrap the building. On the back side of the building, there is a steel plate concrete shear wall core for the elevators and the vertical transportation. It's about 2 miles from a major fault in the Southern California region, the Newport-Inglewood fault. So this building is very complicated. And we essentially had to tell the engineer record that we probably didn't know how we could ever approve such a building unless it was base isolated and we could make the rest of the system elastic. Everything above the isolators is designed to be elastic in the earthquake. And that was about the only way we could ever imagine that we would understand the behavior of the building well enough to let the project go forward. So anyway. All right, so finishing up part 1. Sorry, this has been going a little far longer than I wanted. It's the longer part, but some interesting challenges on similar projects. The performance-based guidelines give us a mechanism to make this all happen. Takes a great interaction between the engineer record and the peer review panel. We're continuing to update these documents from what we learned on past projects, and helps us to be innovative and really a lot of fun on many of these projects to be involved with those. Plug my battery computer from, I gotta plug it back in. Okay, so let's jump on to part 2 on taller, older buildings. So there was an article in the New York Times in April of 2017 that was called San Francisco's Big Seismic Gamble. And it focused on some of these older tall steel buildings or tall buildings in San Francisco and the fact that they may be vulnerable to significant damage because they had been designed prior to the Northridge earthquake, prior to the present standards that we're using. And this led to a lot of analysis work for us. I sort of joked that I should have sent a couple of cases of wine anonymously to the author of the person who wrote the article in the paper, because we ended up getting a lot of very interesting projects as a result of this newspaper article. So think about San Francisco and steel buildings in 1906. Earthquake, the buildings that really resisted the earthquake without collapse were steel, sort of moment frame type buildings that are different, obviously, than what we do today, because they had brick infill, riveted steel frames, those sorts of things. We'll talk about that. But really, we thought that steel buildings were sort of the best for earthquake performance. As we kind of went into, as we go through, we see the design of these buildings changing over time. They did start out being sort of composite brick exterior walls with steel riveted frames that were designed primarily for wind forces. But they did well in the 1906 earthquake, and engineers felt like they could continue to do well. So then the process has changed in the 1950s and 60s. And we got away from using the masonry for the perimeter systems, and we went to more fully steel systems and with all bolted connections. So there wasn't any field welding available in the 50s, and so there was high strength bolting though. So all the connections, whether they be beam column joints or column splices, were done with bolted connections. Many times these were dual systems where the engineers would put concrete walls around the stair towers, the elevator cores, et cetera, to get sort of concrete and steel resisting the earthquakes. That didn't change. Oh, sorry, it kind of had a, odd, it doesn't want to. Okay, so the 1960s, we continued to change the design of those buildings, or engineers did, I wasn't around at that point, to now start to incorporate welding in the connections. And in the early to mid 60s, the connections of the beam column joints were fully welded, where we welded the connection of the column flange, the beam flanges to the column flanges, and as well as the web of the beam into the column face of the column. We also had column splices that started to be welded. Most of those column splices are what we call partial penetration splice welds. So they didn't weld the full thickness of the steel across the splice, but just part of it. And that's created some problems for us as we go forward. So as you continue to move into the 1970s, people would, and in the 60s, people would make moment connections at every beam column joint in both directions. As they moved into the 70s, they started to just do more perimeter systems. And then they went to a bolted connection. This was tested at Berkeley in the early 1970s and seemed to give pretty good performance. So engineers found that this was a more economical system than the fully welded system. So they weld the flanges, but then bolt the web connection. And so it's a little more economical. So engineers went with that direction in the 1970s, continued to have those partial penetration welds. In the 80s, we really started to see much more of the perimeter system, where the interior columns would just be for gravity loads, and you'd see more perimeter type moment frames. So now you're sort of getting less redundancy in the system. You're getting larger members, larger connections, larger columns, larger welds, etc. And also in the 80s, we found that this was at the first time when it was available to engineers to really be able to to do linear elastic analysis on, larger structures with computers. And so engineers got a little more aggressive, I guess, with what they told architects they could design for, because now they could put this kind of a frame into their elastic analysis model and allow things like transfer girders. You can see this is a hotel where closely spaced columns in the hotel floors, but then when you get to the banquet levels and meeting room levels, they wanted more open ballroom space. So they took out a bunch of columns with transfer girders. So you've got some changes in the lateral system now. Here's one over here on the left where they had to have an open space. So they put a couple of diagonals to transfer a column out. These kind of irregularities aren't really friendly to seismic response and performance. So, these are some pretty challenging things to deal with when you have to do a nonlinear analysis. So we thought everything was fine and dandy with all of our designs until the Northridge earthquake in 1994, when we had a number of steel moment frames of this bolted web welded flange type of construction that had column fractures, beam fractures. And so you can see a couple of examples here where this is the beam flange, this is the column flange, this is the web of the beam. And literally a chunk of the column flange was pulled out by the earthquake in a fracture. Here's another one where the beam flange is here to the left, column flange is standing vertical, beam web. You can see the fracture almost all the way through across the entire column. This created, and this one building here was torn down on the right. It did have that residual drift I talked about earlier. In the first story, it was about 4 inches out of plumb. It was only a 2-story building, so they basically tore it down. But we were able to reproduce some of these fractures in the lab with research right after the earthquake. And that's really sort of set the steel industry on its ear a little bit, trying to understand this, and really changed all of our building codes for new construction. And then the existing building, there weren't really any standards at that time. They were starting to be developed, and now we're working with some of the existing buildings. So one of the things we found in doing these studies is that different challenges are presented by the different structural systems used by the engineers at the time that they were built. Some things were better in the old days, some things are better now, and really makes for some interesting analysis work to try and understand the performance of these. So some of the things that we found in studying some of these buildings are that typically you do not see the deformations spread out over the entire height of the building. It's usually in these taller buildings, you're usually going to get a series of stories, maybe a quarter of the height of the building. A lot of times it is in sort of the middle third from second mode effects, where we see some of the major demands. And this is some of our software where the different colors kind of tells us where the heavier demands are. So red is obviously the most heavily demanded area. One of the things that's probably the most important thing is that the response of these buildings is very sensitive to ground motion characteristics. We find that in this case, here's 11, or is it 11? I don't know, 2, 4, 6, yeah, 10 or 11 ground motions. And basically for the same response spectrum or demand, this is why we do multiple ground motions that supposedly characterize the same earthquake, because they can really impact the building very differently. The graph on the bottom is what we call the interstory drift. So how far the building moves. And in this case, you can see the maximum is almost 3%. The mean or the median is, I think, here at something like 1%-ish at that same story. And there's a whole spread. Part of this is because we have a system that's a fracture and non-ductile type of response. So it's much more susceptible to changes in ground motion than if this was a very ductile system, say hopefully the way we're designing them today. where we're controlling the response and we've got the inelastic deformations well controlled, this spread would be much smaller and we would see a much tighter, and that's what we see in the new building designs, that we don't get this kind of widespread that we have on these less ductile systems. So a little more about ground motion intensity. One of the things that we've also learned is that, you know, what we do is when we look at the very large motions, and if we say we just barely meet the criteria, we say, well, gee, what if the ground motion was 10% greater? You know, the earthquake doesn't know it's supposed to be exactly the ground motion that we put into it. In many cases, there's sort of a cliff. Once you hit the capacity and it gets just a little bit bigger, the deformations can go just, you know, get out of control very quickly. And this is sort of a graphic there, where in this case, the median response was at the targeted acceptance criteria demand was about 1.6% at the most, and then 10% bigger was 2.6%. So it very quickly, so these are the kind of buildings that we really watch out for in developing retrofit designs. Another thing that's important, obviously, is how do we model the connection fractures, because they are susceptible to this fracture that we saw in Northridge. What we've found is that in many cases, if you just have connection fractures, in most cases, we don't think it's going to take the buildings down. And we saw that in Northridge. None of the buildings collapsed that were damaged. And because there's a lot of other things that help in the seismic response, but we do need to be very careful about how we understand the models. And we tend to do these fracture models, which are kind of graphically shown here. And when we do the fracture models, we use fibers to pick up the fracturing of the connection and to mimic the response that we found in some of those tests that were done on the pre-Northridge connections. So irregularities in buildings, I mentioned that in the 80s when engineers got a little more bold when they could do analysis. Those can change the response a lot. You don't see it in the elastic analysis, but in the nonlinear analysis, especially in these non-ductile buildings, it really, the earthquake finds the vulnerable part of the building, and it really focuses the demands there. And so what we've seen here is when you have some transitions in strength or stiffness, that you really end up targeting a lot of the displacement demand on those stories. So it, again, much more important on these non-ductile structures than on our newer ductile structures. We've also found that linear analysis is not a good predictor for these taller buildings, the non-ductile buildings. In the case, the linear analysis shown on the left, nonlinear analysis is shown on the right, and you can see just very different characteristics or predictions of the response of the buildings. The other thing that can be very important is the toughness of the weld metal that's put into the connections. If we get above a certain level of toughness, the fractures probably don't occur. Unfortunately, the weld metal that was used in the 70s and 80s, the older buildings had better weld material, newer technology that allowed welds to be made faster was not as good in the 70s and 80s. Now we're requiring that new technology to have a high level of toughness in all the new welds that we're putting in. But changes in the weld toughness can definitely change the response of the building. And we see that most importantly in column splices. Again, I mentioned that many of these buildings had partial joint penetration column splices. Those are also susceptible to fracture, especially when you have low toughness weld metal. And we really feel like this is the primary thing that could potentially cause one of these buildings to collapse, of the column splices. And we've seen that in the models that we do. We actually do fiber models of our column splices to pick up the fracture. And that is where we see the biggest demand. The building on the upper left was from what they call the Pina Suarez Towers in Mexico City in 1985, was brought down by column issues. Very different from what we do in the US as far as at that time in Mexico, as far as the type of columns and the configuration of the columns. The other pictures on this slide are from the Kobe earthquake in 1995. And interestingly, and they use box columns there, which we don't use too often in the US. But here's a case where the column splice fractured and actually sheared and moved. And luckily, it landed on the column below and had some deformation, but didn't collapse. I don't know if I would have walked in this building and taken that picture, but anyway, this is pretty scary, right? If you lose a column splice, that could bring a building down. So safety on older moment frame buildings, we think based on our studies, we think the likelihood of collapse if you're in a sort of a 225-year hazard or less is quite low. We start to see issues around the 10 and 50, the 475-year earthquake, which is about where our new buildings are generally designed for risk category 2. But when we get to the larger demands, the 5 and 50 demand, about 1,000-year return period, then at least our models right now are saying there's a pretty high probability of having some real challenges for these buildings. So trying to fix these buildings is not simple. If you do have a bigger earthquake, repairing them is going to be quite difficult. There's this question about aftershocks, and if you have to evacuate the building and everything around it, repairing while something is occupied can be a challenge as well. And there's again a lot of uncertainty in what we're doing because of this non-ductile behavior, lack of knowledge about the actual construction of the building and toughness of weld metal, etc. We've had some interesting retrofits that we've done. This one here is a nice one to talk about. And so this is one of these moment frame buildings. The owner wanted to do a phased retrofit over the life of over about a 15-year period. We were able to convince the city of San Francisco that at every different phase, and there you can see some of those graphically in the colors here, that the building was getting better than it was before. And so even though we sort of hopscotched around depending on the changes, this is an office building, and when the leases come up, they're going to evacuate the floors for a period of time to do the retrofit before they bring a new tenant in. So that's sort of their long-term plan. And the city allowed this to happen. We're through about 4 phases of it now, and there's a couple more to come. So it's a way to keep the building, occupied and used in the process, a long-term kind of retrofit approach, rather than telling an owner you have to evacuate the whole building to do a retrofit. They could lose all their tenants and it wouldn't be a viable project in the past. So so just finishing up then, practice has changed a lot over time. We have new tools, new technologies for construction. Our analysis is a lot better. Our understanding of ground motions is a lot better. Buildings designed prior to 2005 were pretty much on elastic procedures. A lot of what we're doing now is this performance-based design, directly looking at nonlinear response. So we need to worry about these older non-ductile buildings, not just steel, but concrete. I focused on steel here because of the ones we've been studying. But we feel like the things we're doing now, new construction and the peer review processes, that we are getting much better, or hopefully going to get much better performance in the future. And so with that, that's the San Francisco skyline recently with the new Salesforce Tower, which is the tallest building in San Francisco there in the center. And let's see, we're right at 11:30. So I'm happy to take some questions now. If anyone's got a few questions, if people want to do stuff in the chat, we can do that as well. Where's that at? I'll stop share. Okay, so if, is it better to do, use the chat, or I guess people can just fire away with questions if they have them?
Yeah, either way will be fine, I guess.
Okay,
People can unmute themselves.
sorry for, I know there's a lot of material, but
And Dr. Sutley has a
hopefully,
question.
I
hopefully,
do have a question. Thanks, Jim. I really
Yeah.
enjoyed your presentation. So my question is kind of in two parts, and
Okay.
that's, there's a lot of work coming out of EERI and SEOC and ATC and NIST and some of the other organizations you mentioned earlier in your talk on designing for functional recovery.
Sure.
Right. So can you speak about how like performance-based earthquake engineering for tall buildings intersects with the design for functional recovery?
Yep.
And then, how does this intersection maybe get more complicated with the kind of lack of confidence that you have in residual drift estimates?
Good question. So residual drift. Yeah, it's a great question. So functional recovery is it's a very exciting thing actually for the engineering profession at this point. For us, especially in California, we had we have a lawmaker from Southern California, Lewin Nazarian, who is very interested and engaged with EERI, the earthquake engineering community. And he latched onto this concept of functional recovery and brought forward some bills to our state assembly that haven't made their way to full votes and to like be implemented into the California Building Code. But we're hoping that kind of as this next cycle of the legislature moves forward, that we can move that forward. So the idea with functional recovery is, and I think I've just mentioned once at the start, that our building codes have been developed over the last 75 years based on the concept of life safety, right? It's good enough if we get that big earthquake, if everybody gets out, maybe the building can't be repaired. It may have to be bulldozed, right? But that's okay. Now, that we're not sure that all of society agrees that that's appropriate, right? I mean, it's economically, it makes sense to try and make every single building like a hospital. Could really make construction costs, a very difficult to work through, not to mention all the challenges with the existing buildings. So this concept of functional recovery is about, can we design buildings a little bit better such that in the earthquake, they may be damaged, but they can hopefully return to service. They could be, hopefully if there's repairs that are needed, they can be done while occupied, those sorts of things. And no guarantees here, but really just sort of increasing the resilience of each building one at a time, which is really about sort of community resilience, right? If our buildings are going to be better, and if we can have resilience in our systems, like our water and power systems and things like that, then we can recover from a major event like a big earthquake much better than what happened in Katrina in New Orleans in the 90s or 2000s, I guess, 2005. So that was not a resilient community in New Orleans, right? So that's what we're trying to get at with this functional recovery. So it's a great thing. There is a great overlap between performance-based approaches and design for functional recovery. There's a simple man's functional recovery, which is just make the building stronger, and that goes a long way to it. But to really understand the performance, you need to do the performance-based design on top of it. So I think most engineers, if this, and hopefully we'll get to this, if we can move forward into that world, I think that will be a boon for doing a lot more performance-based design, because it's adding more steel, more concrete to the building adds more cost. If we do more analysis to demonstrate that we can get to that functional recovery performance without adding a lot more steel or concrete, the owner saves money, the community saves money. So I think there's a definite overlap there. The residual drift issue is a challenge. There's no question about it. There are some systems that may be a little more susceptible to residual drift than others. I think that some of that has maybe been a little bit overblown by the researchers that have looked at this because they're thinking about simple models of just the primary lateral systems rather than the building as a whole. And there's a lot of stiffness in the buildings that we don't calculate from our gravity elements and things like that, that could help to, alleviate that concern over residual drift. It's an area that needs a lot more study, research, evaluation of buildings, and I think we've tried to be pretty conservative in setting the limits for residual drifts, because again, residual drift it's residual, so it's not the building hasn't collapsed, right? But it's whether or not the building department or the owner would allow people to go back into the building afterward. And I think in some cases there will be situations where the building department will say, no, you can't, either you fix it, you have to fix it before you go back in, and we may have to evacuate around there. So it's a dicey problem that we don't have a great answer to yet, unfortunately, but at least we're looking at it now. We didn't even look at it before, which is a step forward. Okay, let's see. I have a question here, I think. How to model outrigger systems, some details. Yeah, it's so the outriggers go into, I don't know if it'd makes sense to maybe go back to, I don't know if I can remember where that is, but let's see if I can. It doesn't seem to want to go back. Oh, I'm not sharing anyway, right? But am I sharing or not? Okay.
Not sharing right now.
Okay, then forget it. We won't worry about that. So the outriggers, so they go into the structural model then. So the columns now are in the lateral model. As I said, in many cases, there's a diagonal element, a brace that's a BRB, typically to control the demand on the outrigger columns, goes into the model, the connectivity, that all gets added into the shear wall element or models, if you will. And then we check that column for the maximum forces that get delivered to it in the earthquake, because it's one of those force controlled elements. The BRB, we check the deformations and make sure it doesn't get overloaded, and the like. So we just add it into the system as if it's part of the primary lateral system. Oracle Park. Okay, what are the challenges posed in stadium design not seen for typical buildings? I think the biggest challenge is that the fact that in many cases, so football stadiums are a full circle, right? Baseball stadiums sometimes are, sometimes aren't. It's that the fact that it's sort of goes all the way around, and it's sort of a three-dimensional system. And again, the primary way to deal with that from an engineering perspective is to break it up into smaller chunks that are easier to analyze and evaluate, rather than to try and tie the whole thing and the whole building together. One project that we were involved with, not as the engineer of record, but as a consultant to the steel erector, was the new SoFi Stadium in Los Angeles, the LA Rams stadium. Very interesting, again, near LA airports and not too far from one of the major faults. The idea was the architect wanted to put not a sort of a plexiglass roof that would let light come through it, but the people in the stands wouldn't be, would be in the shade, so to speak. And so the engineer had to design a system with basically an ellipse that was 1,000 feet by 500 feet, with 40,000 tons of steel 100 feet up in the air to support this tensile grid, if you will, to hold these plexiglass panels up. And they were really concerned about the seismic. So what they did, I thought it's a brilliant engineering. It's going to win a lot of engineering awards now that it's finished. But they have 40 columns that go around the perimeter of the building. And rather than isolating at the base of the building, they isolated at the top of those columns. So that 40,000 tons of steel is going to slide around on top of the columns when the earthquake hits. And otherwise that building would want to tear itself apart because, you know, when a building is that big, the ground motions are different at one end of the building than the other. So that, you know, they could be tearing itself apart. So this really created a much more efficient structure. It was hard as heck to build for the erector because of the, you know, the isolators being up at the top of that 100 feet up in the air, which is why we had to do a lot of engineering to help them just get the thing in place. But when the earthquake hits, I think it's going to be a really great performance. Okay, corrosion deterioration, existing steel buildings and rebar, particularly in the cold regions. You account for that effect in structural modeling? Good question. So do we account for, you know, kind of existing conditions? And the answer is yes. Luckily in California, we don't have freeze thaw cycles and things like that. So we don't see a whole lot of corrosion issues, but yeah, when we do, we try and model for it. The ASCE 41 standard for seismic evaluation and retrofit requires us to do a survey of the building. And if we see some issues, we have to dig deeper, literally, to figure out what the impacts are. And, you know, we would, a lot of times, part of the retrofit is to fix the deterioration, right? I mean, you want it to stop the corrosion, and then also repair it as well, so that you can kind of bring it back to the original. But sometimes, you know, you can also model it if you want, and maybe in some cases it's bad enough you sort of just take it out of the structural model for the lateral response. But a good question. We do need to look at existing conditions for sure.
I have a question, Andres Lepage here. How you doing,
Hey,
Jim?
very good, thanks. How are you?
Good. Hey, I enjoyed your presentation, packed with a lot of information. So
Yeah, sorry.
I
gave a lock the presentation, so there's a PDF available if you want to.
Oh, that's great. I got a twofold question.
Okay.
And I'll hit the second one depending on how you answer the first.
Okay.
So, and this is an issue that I know comes up. So basically, to recap, you mentioned that an essential goal in performance-based seismic design is to identify those elements that are expected to yield and design the other elements to remain elastic.
Yep.
Now, in your peer review role, what was the approach taken in the design of the foundations? In other words, are foundations designed considering the overstrength of the superstructure?
Yeah, good question. So yes, they are. And we don't, in typical code design, especially in steel, we use a capacity approach, right? We figure out what the pushover capacity of the building is, and then we carry those forces down to the foundation level. ASCE 7 doesn't require you to design the foundation for the capacity. AISC requires you to design the structure to the base plate, the connection to the base plate, and essentially the anchor bolts into the foundation for the capacity. ASCE 7 allows you to not do that. In the performance-based projects, we don't, because interestingly enough, one of the reasons for a lot of the performance-based on taller buildings, and I think I mentioned in one of those graphics, is that to do a full capacity-based design on a 50-story building is way, way too conservative, because the ground motion will never yield and strain harden the entire structure over its whole height, right, to deliver that pushover force, if you will, because it finds, during the earthquake, you can watch the yielding sort of move up and down on a tall building, and it's like goes up in packages of maybe 1/3 to 1/2 of the height of the building. So what we do is we, track the demands at the base of the structure in the nonlinear model. And then what happens is, because it's a force controlled element, we take so say you have 11 ground motions and you want to design the overturning, demand on the foundation mat or pile cap or whatever. You for the 11 ground motions, you calculate or you find the maximum response for each of those 11 ground motions. And then you take the mean of the maximums, all right? So there's 11 numbers and you take the mean of those numbers. And then you multiply that by a factor of 1.3 to try and cover over, making sure you kind of pick up the max of the max, if you will. And so that's the way that we try and capture that maximum demand on foundation elements and all the force controlled elements. We do primarily, and a lot of the engineers for the flexure, they feel like flexure in their mat foundations can be considered somewhat ductile. So they may not go, they may request to not add that 1.3 factor. But for shear on the foundation mat, they always apply that 1.3 factor to make sure the shear in the mat is not controlling. So a little bit of an inelastic behavior for flexure may be okay, but not much for shear.
Okay, so if you do all that, then let's talk about the Millennium Tower. Okay, the Millennium Tower, for those that don't know, is a building that was peer-reviewed and designed following performance-based seismic design and infinite nonlinear analysis. And then the building got in trouble due to foundation settlement for gravity loads.
Yeah.
So has this blunder changed peer-reviewed PBSD? In other words, so if you're telling me that you're designing it for 1.3, the maximum of the maximum, sorry, the mean of the maximum, and apparently it had to be checked for that, but then for gravity can't take it. How can that be explained?
Yeah. Okay. Well, it's a long question. There's a long answer to your question. So actually the building, that building was not a performance-based design. That was the last tower in San Francisco that was code-based. There was a brief peer review done by the professor on some of the rebar detailing because they were very big walls. Like the city plan checker wasn't real comfortable. So he asked this professor who's expert in concrete that you know very well to come in and look at the detailing and make sure that it was, the best ductile detailing and the concrete was done well. No one ever did a peer review on the foundation design. And the other interesting thing about the project was it was originally designed to be a steel frame with a concrete core. The contractor came back to the owner and said, I can build this building less expensively if it's all concrete. That change, and at the time, they had already designed the foundation and the piles for the steel building. That added about 30% to the weight of the building. The geotechnical engineer reviewed their calculations, and this has all been settled. And so I don't think I'm speaking too much out of I shouldn't probably be saying all this.
You're not going to get in trouble, yeah.
Okay. This doesn't go beyond the room, okay, folks? But anyway, the engineer looked at their calculations, said it still should be okay for gravity loads, and the engineer the structural engineer revised their calculations, obviously, for the extra weight and how they detailed the whole structure. And it started to sink while it was under construction, and it sank before anyone moved in the building. It had sank a foot, and it was only supposed to sink 2 inches, total, or settle 2 inches. And there was a blunder in the calculations. There's some claims about dewatering issues with adjacent sites that were under construction. Some people think that was, depends on what side of this lawsuits that you were, whether or not you think that was real or not. So it really was not although I will say, while I will say, I don't think it was really a fault of the performance-based process because it wasn't really part of it. The city of San Francisco now requires a peer review. They require 2 geotechnical peer reviewers, one for ground motion and one for foundation design. And so
that has always been the case, or this is
no, since just in the last few years.
Because of the Millennium
Because of
Incident?
Millennium, they require.
Excellent.
Yeah, but frankly, the ground motion reviewers are also geotechnical engineers, and they were looking at the designs as well prior to this additional thing that the city of San Francisco has done. None of the other cities have gone to that extent. But yeah, it's a black eye, no question, for the process. But no, engineering is not an exact science, obviously. We learn from it. Hopefully we won't see anything like it again.
Thank you.
Okay, yeah, sure. Okay, does any other questions?
Hi, Jen, this is Jen. I co-advise EERI group here. I wonder if you have any advice to students who are attending today, who are probably gonna, follow you as a role model to become a great structural engineer in the future. What are some of the qualifications that you think are important for young engineers who wants to do the job?
Sure. Yeah, it's a great question. One of my favorite parts of my job is being involved in our hiring young engineers out of graduate school. We focus on people with master's degrees and some PhDs, primarily because we do so much earthquake engineering, and a lot of that kind of material doesn't really get brought forward in academic training until graduate school. The things that to me, the most important thing is obviously we look for people that have good grades and, have some internships are great with either, engineering firms or general contractors or things like that. So you're kind of seeing what the process for design and construction is like. Taking all the right classes, grades, being involved in, groups, the professional groups on campus and stuff like that. One of the things that we're really interested, I personally am really interested in, is, and it's hard to describe, but it's not like a technical thing or anything, but it's like, how engaged is the person? Do they have a spark where they're really curious, right? Whether they really want to understand things, and are they going to be the kind of person? Because one of the great things about the engineering profession, I'll tell you, I tell people this all the time. One of the bad things is that you're not going to get paid enough with a great idea to patent it and make millions of dollars and buy an island in the Caribbean and retire at age 30. Okay, that's not going to happen. It's a career where you get to but the great things about it is that you can learn things and improve your value and your ability to contribute to your clients, your company, the community more every day for your whole career. I mean, things that we're doing now, I wouldn't have dreamed about, when I first started. And it's even, more and more, we're just doing more and more better engineering all the time. So that's exciting for me. And seeing someone that is going to, kind of go up that ramp, right, and continue to learn and really wants to continue to, explore and is inquisitive, right, and asks questions like why questions, and more than I don't want someone that just wants to give me an answer. I want them to figure it out, why it's important, and and the kind of person that's going to, like I said, continue to grow throughout their career. And trying to find those people is, in my mind, probably the most important thing for a successful engineering career.
Thank you.
Sure. Okay, other questions? Okay. I don't see any more on the chat. Anybody else? Okay. Alok, I'll turn it back over to you.
Yeah, okay. There does not seem to be like any more questions. We can, you guys, if you want to like hang out, be in here for a while, interact some more. Jim is available for another hour or so. But yeah, either way.
Yeah, sure. I blocked off my schedule, so I'm okay to have more questions like John's. Certainly those kinds of things. And if you have questions about EERI or about other things related to the profession or what it's like to work in offices, I'm happy to answer them.
Yeah, Jim, I had a small question. The softwares we use for like structural analysis is just limited to ETABS and SAP and all. But are there any like preferred softwares for RC frame structures or steel frame structures that are like more commonly used?
Sure, a good question. Yeah, obviously there's a lot of different software out there. Certainly SAP and ETABS are, we do a lot of work with the CSI suite of software. There are some specialty, certainly the primary ones. The other one is RAM is a big one that's used by a lot of firms. There are some specialty firms or specialty software for concrete and especially pre-stress concrete that are available as well. For nonlinear analysis, most in the profession are using another CSI product called Perform 3D, which was developed at Berkeley originally back in the, I guess early 80s, I think, the basis of it. And then it's CSI sort of built it up to make it a commercial software. So that's the primary tool, although CSI is trying to push ETABS and SAP into the nonlinear world and give it some of the capacity that Perform has. Many of the engineers are a little nervous about making that transition because of the solvers are different. The other thing that we're looking at right now is, there are full-blown finite element analysis programs like Abacus and things like that that are not as effective for frame analysis. But one of the things that we're looking at now is looking at OpenCs, which is, obviously has been developed at the research level, but it really hasn't made its way into the commercial market because of the input-output issues and the like. But it's very powerful. Some of the solvers are amazing, and it's got pretty much everything that we could ever want to use. But we've been working with a couple of companies that have been working on that site, and we're hopeful that in the next generation, working with OpenCs and some of these programs to help with the input-output part of it will become a tool that we can use too. Maybe it won't be for all the projects, but for some of the projects where we need some real special information, it could be a good thing for us going forward. So that's another area that, the software is going to continue to change and get better. and how do we take advantage of it as businesses to understand the performance of buildings better is really interesting for us to try to figure out. Yeah, the other thing that's been amazing to me is the dealing with all the data, right? I mean, we've had runs that have had 2 terabytes of output to deal with. And how do you pick out the pieces of that data that are most important to you, right? And so a lot of our engineers now are doing Python scripts and coding to try and, you know, go into the data and pull things out efficiently and do, you know, the graphs and things that I showed, all that stuff. So that's a new tool or a new skill set that is helpful to us when engineers get out of school, right? I mean, we don't. Some of them are do it on their own and things like that, but we're seeing more and more need for that because the models are getting so much bigger and more complicated. So some of that coding skill can be, and I joke about the animal software. It was Python, Grasshopper. I think there's one. What's the other one? Rhino, or some modeling tools that we use, and yeah, being able to converse between the analysis software and some of those, and use some of those techniques for modeling, 3-dimensional modeling, is really gives you this ability to do those crazy projects like that wrapper tower that I showed down in Los Angeles. You know, you could never even imagine doing anything like that without the kind of software we have now.
And how much is IDA, incremental the dynamic analysis integrated into all of this?
Yeah. Okay. So for those of you that don't know what IDA is, incremental dynamic analysis, the idea there was it's a really interesting concept. The idea is to, when you're testing a structural system or a structural model, to take the ground motion and then run the analysis and get your results, whether it's interstory drifts or whatever. And then you incrementally increase the ground motion, just amplify it by 5% or 10%, run the same ground motion, and you keep doing that until you find the building, you know, collapses, if you will, or it can't take the interstory drift anymore, and it kind of goes off and shows a modeling, like the collapse in the model. And then you do it for a whole suite of ground motions, right? And you do it for potentially a whole sensitivity study on different, you know, modeling issues that you had to make decisions on. One of the things about nonlinear analysis is the number of modeling assumptions we have to make is probably an order of magnitude more than we do with elastic analysis. It's sort of the how you model the nonlinear response. Do you model the pinching hysteresis? And you do that. There's all kinds of different things that can affect the overall response that your model predictions will give you. So so IDA, we don't use it too much in building design for the performance-based designs. Where it comes in handy is if someone wants to come up with a new system and then they implement the P695 procedure from FEMA that I was sort of mentioning. That's where people have to do IDAs. And the idea there is we have a new system. We do what you call designing archetype buildings. So you know, number of stories, footprints, you try and cover the space that you think the building could be used. And you design those buildings with this new system, and then you subject it to the ground motions and you do the IDA response. And there's all kinds of tests to make sure it's meeting the criteria to qualify as a new system. And that's how, in the old days, that's how we would, today, if you wanted to have like a brilliant idea for a new structural system that you wanted to get into ASCE 7 someday, that's how you try and validate it with the analysis. You also have to do tests on connections and things like that to make sure that you've got everything squared away. back in the old days, it was a smoke-filled room, literally, right? It was the committee smoking cigars and cigarettes, arguing over R factors and C sub B factors and omega factors with very little research to go through, very little analysis, but using engineering judgment, right? So we're trying to bring forward the tools that we have now to be incorporated into discussions or decisions about, the new systems and how they get incorporated into the building codes. There's still a lot, the rooms aren't filled with smoke anymore, but there's still a lot of engineering judgment that comes into it. But this is now a key thing for us to make it consistent for all new systems to come forward.
Okay, yeah.
Yeah, I'm gonna stop the recording here just since unless someone else has another question, actually. I'll just hold off on that.
Okay.
I have a quick question.
Sure.
Sorry. Hey, Jim, thank you for your interesting presentation.
Sure.
My name is Amin, and I am a PhD student here at KU in structural engineering under supervision of Dr. Elena Sot-Lee, and I'm working on functional recovery things.
Okay.
And actually, my background is in earthquake engineering. I did my master in earthquake engineering back home in Iran, and 12 years ago, I guess I got graduated from a master, and then since then I've worked in different engineering companies. So I just wanted to ask you a question because you mentioned about the columns that are close to core walls in a system, in a tall buildings, that can be very challenging for to consider them and design them, and also about the diaphragm. And I can remember in one of the projects that I was involved, and it was a big and huge challenge to design the diaphragm, the collectors, and control the forces there. But you didn't mention about the beams that are connected to the walls, to the core walls in the system. So I guess that can be a big challenge too. So can you?
Sure. Yeah, so in two ways. I didn't get really detailed on collectors and things, but those beams that are connected to the walls will act as the collectors to bring load to the walls at each floor, to transfer the inertial force. And then when those beams are connected to a column that's close enough, and and you'll get that what really it is it's an unintentional outriggering. So when the shear wall goes this way and the tension side wants to lift the floor locally around it, but the column's over there and it doesn't have any tension on it, but there's a slab and or a beam that's connected to the column and connected to the wall. It forms this little frame action, and then that's what creates the challenges for the outriggering of those columns. So that beam has to also be designed for that. So the rule of thumb for that engineers are using is generally those slabs are in the concrete core wall buildings are about 8 inches thick. And so what they've found is that if the columns are at least 15 to 20 feet from the core, the amount of outriggering is very limited. So, but what they do is, and most of these are flat slabs, so they don't really have beams in them, right? But in the flat slab, they will design the slab in that region to have extra rebar so that it's got the ability to, if for some reason there is some demand there, that there's ductility in that slab to hold the gravity load up and allow some rotation at the face of the column, and then not overload the face of the wall, and then not overload the column because there's some release of that demand there in the slab rather than kind of pulling it over to the column. So yeah, I mean locally you have to worry about the collectors, and then the the rotational issue between the flat slab and
The flat. Yeah.
wants to lean up. So.
And I guess that can be more challenging when you have a reinforced frame concrete structure and then you want to retrofit it by adding some shear walls to, you know, decrease the level of demand on the
Right.
on the frame. Then
Sure.
Yeah, it can be very challenging.
Yeah, no question, right? Yeah, if you're local, so if you introduce a shear wall system into a moment frame, yeah, it changes the whole set of dimensions of the moment frame, which it originally wasn't designed for. So yeah.
Anyway, thank you for sharing your experiences and
thanks.
interesting presentation. Yeah.
Yeah, thanks. My pleasure. Yeah, actually, the seismic retrofit in many ways can be more challenging and more interesting than new design. And the reason is in new design, you're working with an architect, right? And you can kind of get the architect to help you get a good seismic system in the building, right? When they're designing the layout of the building and the configuration and all what they need to design. The existing building, you're stuck with what's there, right? You've got a lot more constraints on how you can deal with the building than when you're designing it, if you will. So yeah, the existing buildings are a lot of fun because they're no two are alike either, right? And you have all kinds of different challenges going forward with those. And historic buildings are even more challenging because you can't mess up the historic character or the features of the building, and trying to work your way around those and still get a good lateral system in there. It's very interesting, very fun. So. Okay.
Hi, Jim.
Hello.
My name is Ram Majumdar. I am working as a postdoctoral researcher with Dr. Shatlis here.
Okay.
Before that, I have a master's degree in earthquake engineering as well as a PhD on civil engineering. My interest here, like in our group, we are working on community disaster resilience analysis. So we mostly try to focus on the building analysis on urban scale and try to prioritize different buildings.
Okay.
So when we are performing seismic hazard, we are assigning different archetypes for the buildings located in a city.
Sure.
And we are using the Hazu's fragility curves, but there are a lot of uncertainties because we only assign building archetypes depending on the building structural type and the story heights only, but we don't consider other uncertainties regardless of whether it is infill might have a defined types of structure and other uncertainties are there. So I would like to know your feelings that when we try to perform this community disaster resilience analysis in urban scale, how to minimize the uncertainties in the performance analysis?
Yeah, that's a great question. Wow. Yeah, you know, the more detailed you can be in the distribution of buildings by type and height and age, the better, right? You know, I've heard of, you know, people using like Google Earth to try and get a handle on the distribution of building stock and, you know, in cities and things like that. Certainly that can help. You know, some of the uncertainty you can reduce by doing more and more Monte Carlo type simulations, right, of your analysis. So you guys know more about that than I do, but that's one way. And again, trying to, because HAZUS only has some limited number of things that you can fill in, and you know, the better your information is on all those items, the better your evaluation is going to be. So I think that's important. You know, we're getting some tools to be much better at or that can be much more detailed on a building level, right? There's the FEMA P58 project that was really performance-based design, earthquake engineering design, and it incorporates the structural system and the non-structural elements, and and all that. And it has fragility curves for the ceilings and the walls and the cladding and all the non-structural elements, the equipment that's all put into the model, if you will, to try and estimate, well, they used to call it death, dollars, and downtime, right? But they use different terms now. But so, it's potential for collapse, which is more the structural part. But then the dollars, how much is it going to take to repair? And then probably the hardest thing to estimate is how long a building will be occupied, right? Or before it can be reoccupied. So that tool is being further developed by a company called HB Risk. Kurt Hazelton is a professor at Cal State Chico. He did his PhD at Stanford. And Jack Baker is the B from Stanford. And so they have taken the FEMA P58 engine, if you will, and turned it into a consulting tool. And people are they can do portfolio analysis with it. Maybe not on the community scale yet, but certainly on the small numbers of buildings. And I'm sure that they're looking at larger scale work too. Not that close to the urban level analysis work, right? Because we're sort of building by building. But I know that NEERI, the Sim Center is really involved, and maybe you guys are working within that framework or that organization. But I know the Sim Center has a lot of effort going forward at sort of regional estimates and response. And yeah, I think it all fits together, right? We need to have a community scale analysis, recognizing that there's a lot of uncertainty, and then the uncertainty hopefully gets smaller and smaller as we get down to the building level. But there's still a fair amount of uncertainty even in the buildings too, right? So one thing that we'll never be certain about is what an earthquake's going to throw at a building. I mean, it's we just don't know what the ground motion is going to be, going forward. So we have to recognize our estimates are uncertain at best. Yeah.
Thank you.
Sure. Yeah, good question. Interesting stuff. I know Elena's group, I know Elena from doing some work with the NEERI Users Forum, and I know you guys are doing some really interesting work. So that's good.
Yeah, I think that's about it. Almost everyone's
Okay.
ability.
Sure. Okay.
Yeah, it was wonderful, Jim.
Yeah.
You
No
speak
problem.
about
My pleasure.
Yeah.
And if anybody does, want to ask further questions, Alok, you can give them my email address, and they can, can follow up with them. Like I said, I'd love to be there today and, have small group discussions and things like that, tour around the facilities and labs and stuff like that. But
you have already been here, right?
Yeah, I have. Yeah, it's a great campus. Yeah, it's so.
It would have been a different experience altogether, but never
Sure.
mind. Yeah.
Sure.
But
Okay.
if it's that, then yeah, everyone, thank you for attending.
Sure. My pleasure. And thanks to both of you guys for organizing. And I guess it went off okay.
Yeah.
Good. Okay. Very good.
It was all right. Thank you, Chris.
Yeah, thanks, Chris. Good to see
You guys took care of most of it, so I didn't do much except send the link. So thank
yeah,
you.
I'm glad. Just getting the link was important.
Yeah.
So I was just looking at it, and there was a note in there that says the link is inaccessible even to the speaker a minute before the presentation. So that's why you had that trouble.
Oh, okay. Okay.
It did say just send.
Yeah, it's like it said you need a password. I said, wait, they don't have a password.
I mean, it said right there though, just send them the link. I didn't look at that. I'm familiar enough with Zoom to just know to send a link. But that was, okay.
Right.
This
Okay,
explains.
no worries. It worked out fine.
Yeah.
Great.
All right, great. Okay. Well, thanks, guys. Have a good
Take
rest
care,
of the
everybody.
day and a good weekend, and appreciate it.
Thanks.
All right.
Bye.